Hi everyone, my name is Sonia Martinot and I'm presenting you our work on weakly supervised 3D ConvLSTMs for Monte-Carlo radiotherapy dose simulations. So while you undergo radiotherapy treatment, you get irradiated. And to better target the tumor location and leave the healthy tissues unharmed, your doctors will make a simulation of the irradiation dose beforehand. To do that, the Monte-Carlo method consists in modeling the behavior of sometimes billions of particles to simulate the irradiation dose. This makes Monte-Carlo the most precise simulation tool we have today. However, it is prohibitively time-consuming, which makes it unusable in clinical practice. So that's why we want deep learning to accelerate these computations. To conduct our experiments, we created a dataset comprising Monte-Carlo simulations of 50 patients. Each patient has a set of noisy simulations, so computed with few particles, and a single reference dose simulations computed with 100 billion particles, and which took for each patient 4,000 hours to compute. So we focused on the potential of a recurrent deep learning framework called convolutional long short-term memory cells, or ConvLSTMs. ConvLSTMs are interesting because they extract meaningful features from both the sequential and spatial nature of the inputs. Our model is simply composed of several ConvLSTM cells stacked on top of each other. The model is meant to handle three-dimensional input data and is fully convolutional. And the goal is for that model to learn to produce a fine-grained dose volume, which is supposed to be similar to a precise Monte-Carlo simulation. And it's supposed to learn that from a sequence of noisy Monte-Carlo simulations. However, the reference dose volumes are extremely expensive to compute. So we decided to train our model in a weakly supervised setting called noise-to-noise. Unlike supervised training, the noise-to-noise training scheme does not require to compute the reference dose for the patients that are in the training set. In other words, when you train the model weights are optimized using only the noisy simulations that were computed for the patients in the training set. And the reference dose is kept for the test time. In our case, we optimized our model using a weighted loss between the structural similarity index measure and the L1 loss. And during training, the loss is computed between the model's output and another noisy simulation of the input patient. So to benchmark our model, we compared it to a model called BioNet, which achieved state-of-the-art results last year in several medical imaging tasks. We adapted it to handle three-dimensional data to match our model. To evaluate the models, we computed a metric called the gamma index passing rate, which sets the golden standard for clinical use. And with respect to that metric, our model performed better than BioNet. So the gamma index passing rate indicates the percentage of voxels in which the dose matches the reference dose. So for a better understanding, you can look at the GIF. The GIF displays on the first row the outputs of the different models and compare it to the reference dose. And the second row show you the voxel view of the gamma index passing rate. So simply put, when you look at the gamma index GIF, when you see blue voxels, it means that the dose in the voxel is accurate. And red means that the dose does not match the reference dose and is therefore not usable in practice. So future work obviously will focus on improving these results to match the golden standard of having a gamma passing rate of over 95%. The code is available online, and thank you for listening.